Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. There is a link to a printable set of guided notes that you can use to go along with the examples that I show in this video. If you're one of my students, you should definitely have the notes printed out. Okay, in this section, we are going to look at velocity and other rates of change. Not that we have not looked at rates of change already throughout the year, but we're going to further our study of them, and we're going to connect them to some concepts in physics. Before we jump into the actual notes, I want to put these formulas up on the screen, and I want to address them because every year when we get to this section, I have students who have already taken physics, and they say that the problems that we're doing could all be done using the kinematic equations. And I say, yeah, that's true. And you're welcome to use them if you are really proficient with them. However, I'm going to get so much hate for this. I like to think of them as the poor man's version of how to do physics, meaning calculus is much richer in how we do our calculations. And so you're welcome to use them. They're there, but they all come from concepts of calculus. And so that's what we're going to look at in this section. Oh my gosh. So many people, I'm sure, will tell me why I'm so wrong in saying that. Okay. So now into the notes. I'm going to move this a little bit because it's bothering me. There we go. The first question is, what is a rate? And a very simple definition for a rate is it is a ratio of two quantities with different units. Okay, you have a lot of experience with rates before now. I put a ton of examples there. Okay, you probably don't want to write all of that down if you are actually taking notes. You can pick and choose what you want. But I wanted to have a ton of different examples to show you that sometimes rates are simple things like speed in miles per hour, right? That's a relationship between how many miles you're traveling per unit of time. But it doesn't always have to be per unit of time. We could have rates in terms of one quantity, say pounds, versus another quantity, say cubic feet. Okay, so again, here's just a whole bunch of examples of rates, and you can pick and choose what you want to put on your notes. Now, usually when we're looking at rates of change, meaning how much one quantity changes versus the other. And a particular rate of change that we need to be familiar with, a particular measure of change that we need to be familiar with is displacement. Have you heard of displacement before? And it's paired scalar quantity distance. Okay, so I have here some definitions. Displacement is the difference between the starting and ending positions of an object. Distance is the total amount of the N and the D got lost there. That's supposed to say ground covered. Don't know what happened. I love technology. There we go. By an object or the total length of its path. So a little example, if it says you were to drive 10 miles east and then 4 miles west, your displacement and your distance would be different. Displacement would take into account the direction of 4 miles west. And so your displacement would be 6 miles because 4 miles west could be counted as negative. Whereas your distance traveled, the total amount of ground covered would be 14 miles, and that means that everything is counted as positive. Okay, we are going to look at a lot of different position versus time graphs of moving objects in this section. So we want to get used to those. And one thing that I want to point out right now, and it'll come up again quite a few times throughout this section, is that whenever you have an object moving and it changes direction, okay, do you see that? There's a turning point there. That usually occurs at a maximum point or minimum point, okay, or what we call the extrema of the graph. But again, we will look at that again. I just wanted to point that out, that you are seeing, this depicted graphically here, where it's moving 10 miles east, and then it turns and it changes position, and it's moving 4 miles west. All right, now let's talk about rates of change. So here we see another position versus time graph, and I have some definitions that you're going to need to be aware of. Velocity is the rate of change of position with respect to time. If you've taken any physics class, you've probably heard a similar definition. Okay, what I want to discuss in particular, though, is that if velocity is the rate of change of position with respect to time, that means it is a derivative, right? A derivative is a rate of change, right? A derivative is a slope. So a velocity is a derivative. Okay, now we are typically going to use the letter S to stand for position. Okay, if we were looking at a position versus time graph, the x-axis is usually labeled as T. The y-axis for position is usually labeled as S. So I'm going to go over here now, and I'm going to call velocity S prime. Ooh, look at that. All right. One other thing to note is that velocity is a vector quantity, and that means that for our purposes, that means that it can be a signed value, meaning it could be positive or it could be negative, and that sign shows the direction of the object. Okay, so like for example, positive could mean moving east, negative could mean moving west. All right, now let's take a look at the definition for speed. Aren't they the same thing, velocity and speed? It's the same definition. It's the rate of change of position with respect to time, or probably a better, definition here would be the change in the distance with respect to time. Okay. Notice though, it says it here, it is a scalar quantity. Okay, it's a scalar quantity. And so what I want to put here is that speed is also a derivative. It's a first derivative of position. However, we typically just denote it like this, with absolute value bars around the velocity. And that means the absolute value of the first derivative of position. Okay, absolute value would take the sign off of the velocity value, making it into a scalar quantity. Finally, acceleration is the rate of change of velocity with respect to time. Okay, what does that mean? That means it's the derivative of velocity. Or, here's something super fun, it's the second derivative of position. Okay, so I'm going to write here A for acceleration. It is the first derivative of velocity, but usually we're working with a position equation, and so we can call that the second derivative of position. Okay, so these are some little relationships between position, velocity, speed, acceleration that you're going to need to be aware of as you work through this section. Two other things that you're going to need to be aware of is that what you are really doing when you find any kind of rate is slope, right? Going back to this picture that I didn't really touch upon very much, if I was asked to find, let's say, the average velocity from point A to point B of this object that's moving, okay, do I actually want to try to draw a line here? What I'm doing is I'm finding, okay, it's not great, but I'm going with it. I'm finding the slope of that line, and the slope of that line would give me my average velocity. Maybe I should say m secant. Oh no, I clicked. I hate when I click. Okay, let me try that one more time. Is our, again, average velocity. Okay. If I'm asked to find an instantaneous rate, a speed or a velocity or something at one point in time, I'm finding the slope at one point, or in other words, the derivative. And we already have that, labeled here, so I think we're good there. Okay, I'm not going to put anything else on my picture is what I'm saying, because I'm running out of room and I don't want to draw another line. All right, so this is really important to keep in mind, by the way, before we kind of move along. You know, so many students get bogged down in all of the details of the algebra or trigonometry, eventually, not in this section, or, you know, like all of the little things you have to keep in mind when doing math. But keep in mind that doing the calculus right now is basically doing the slope, the slope, the slope, the slope, with other calculations as well. Okay. All right. Here I said also, here's something cool that may help you, and I love it. It's a lot of good information about how you can read a position versus time graph and read from it velocity and acceleration. I think it's a little bit too much for now to discuss. We might come back to this and discuss it later on when we have class time, but I just wanted to put it out there for your information. And again, you know, here is another place where this position is turning, right? A turning point is going to usually happen at a max or a min. And, you know, it would be important to also know that when that happens, your velocity is 0. Okay. Again, though, I don't want to get too far into the details here, but keep in mind that this is here. It is a reference for you when you need it. Now, let's jump into the examples. I think these are so fun. I'm going to admit that sometimes I feel a little bit nervous when I do this section because I know a lot of students have already taken physics and you know a lot about physics. And so, you know, then here I come along and pretend to be a physicist and pretend like I know what I'm talking about. And, you know, I kind of do, but I always keep in the back of my mind, I'm not a physicist. Okay, so I always question myself. I'm like, is that right? And I'm usually questioning myself because we're often ignoring things like air resistance and other things that I know in the back of my mind affect our answers. But, you know, what I've learned over the years is most physicists ignore that stuff too. So we'll be okay. All right, let's take a look at example 1 together. And then I'll talk about the different parts. Okay, a particle moves along a line so that its position at any time t greater than or equal to 0 is given by the equation s of t equals t squared minus 4t plus 3, where s is measured in meters and t is measured in seconds. Okay, I'd like to note something that you don't really need to know, but it might help you at some point in your life, where it says a particle moves along a line. That is actually called rectilinear motion. So we do a lot of those examples here in our physics section of calculus. We talk about rectilinear motion. So if you ever hear somebody referring to rectilinear motion, that means, you know, movement along a line. All right. Part A asks us to find the displacement of the particle after the first 2 seconds. All right, so here's what I suggest you do. Anytime you are given an equation to work with, usually you'll start with a position equation, and you need to problem solve. You need to, you know, answer questions or solve problems related to it. First, always ask yourself, what are you trying to find? Are you trying to find time, position, displacement, velocity, acceleration, speed, you know, and ask yourself what you're given, okay? So in this example, we are asked to find displacement, and what we are given is first 2 seconds, or that could be written as the interval from t equals 0 to t equals 2, okay? So what we can do to find displacement is we can go back to our definition of displacement, which says the difference between the starting and ending positions of an object. The difference between the positions. That's the most important. Those are the 2 most important words. Difference between the positions. Okay? So since you're trying to find displacement, you don't need to take a derivative, right? We would take a derivative if we need velocity or speed, or we would take a second derivative if we need acceleration. We're not asked for that here, so we are just working with this function. And what we are doing is we are finding the position of the function at its ending point, and we're taking away from that the position of the function at its starting point. That is a formula that you can use for displacement. Now that you have your formula, it's an easy plug and calculate, right? Plug in and calculate. Let's sub 2 in for the t's here. 2 squared minus 4 times t plus 3. What's that? Let's see. 4 minus 4 is negative 8 plus 3 is negative 1. So I just sub 2 into here. Minus s of 0, okay, that one's easier. 0 squared minus 4 times 0 plus 3 is just 3. Negative 1 minus 3 is negative 4, and let's put units on it. Okay, make our physics teachers happy. It would be meters. The displacement is negative 4 meters. And what that says is that this particle moved 4 meters to the left from its starting point, after 2 seconds. That's what that says. Okay, next, part B. Find the average velocity of the particle over the first 2 seconds. All right, so what are we asked to find? We're asked to find average velocity. What are we given? We're given, again, the interval from 0 to 2. Okay, so the word velocity can mean a derivative, but remember that thing I put the stars beside? The word velocity means a derivative when you are finding an instantaneous velocity. We are not finding an instantaneous velocity because we're not just working with one point in time, we're working with an interval of time from t equals 0 to t equals 2. So we're up here in the average velocity. Okay, to find an average rate, you find the slope between 2 points. Nice and easy. I didn't want to go that much, sorry. Find the slope between the 2 points. That's what we're asked to find here with average velocity. Okay, and so let's just write it out first. We're going to find the slope between, and let's write our ordered pairs. The first time is 0, comma. When we sub 0 into our position, we already did that earlier, we got 3. The second time is 2. When we sub that into our position, we already did that earlier, we got negative 1. Now just do it. Negative 1 minus 3 over 2 minus 0 is negative 4 over 2, or negative 2. And what's the units? We're doing velocity now. Meters per second, right? Negative 4 meters per 2 seconds, or taking that down to a unit rate, it's negative 2 meters per second. There's our average velocity. Okay, so what I'm hopeful of is as we complete problems, we can always just go back to this information, starting here, 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 and taking from it what we need to answer our questions, okay? And then eventually, after you do so much practice, you kind of get good at it and seeing the patterns and, sometimes figuring it out for yourself, hopefully. All right, in part C, that's where we're asked to find an instantaneous velocity, and what we are given is time 2. Now we are ready for a derivative, right? Whenever we are asked to find an instantaneous rate, I'll just go back to the information to show you. An instantaneous rate, you do a derivative. So instantaneous velocity, back to another piece of information, right? Velocity is the first derivative of position. That's important to know. And so we're going to take a derivative here. I'm going to write v of t equals s prime of t. And I'll take the derivative of my position function up here, and I get 2t minus 4. Now, at the particular time t equals 2, I can say that that can be calculated from 2 times 2 minus 4, which gives us an instantaneous velocity of 0 meters per second. Which means possibly that is a turning point. Okay, it probably doesn't stop there and never move again. Yeah, I guess it keeps going. So that would be a turning point since the velocity is 0. Finally, part D, find the acceleration of the particle at t equals 2. Okay, it doesn't use the word instantaneous this time. However, it does only give us 1 point, so we can assume it's an instantaneous acceleration at exactly t equals 2. So again, an instantaneous rate means a derivative, but keep in mind that the derivative we're taking is the velocity, the derivative of the velocity, or you can call that the second derivative of position. So I'm going to write a of t equals s double prime of t. And that's just another derivative from here, which is just 2. That means we have a constant acceleration. We can indicate that we're looking specifically at the time t equals 2. However, there's no t left in our acceleration equation, so we can just write 2 meters per second squared. It's meters per second, right? It's a rate of change of velocity with respect to time, so that's why we have that squared there. Yay. I don't know if you can tell, but I get really excited about this stuff. I like doing it. I think it's fun. Do you think it's fun? All right. Example 1 done. And that was an example where we were looking at a position equation. Okay. Next, example 2, we do not have an equation to work with. We have a table of values. It is still a position function, and it's a function of time. However, again, we don't have an equation to work with. Okay, so we're going to have to use the table of values to get our answers. All right, so we're looking at seconds versus feet versus seconds, and the first part asks us to find the average velocity for each time period. Average meaning we're going to do a slope, right? And we have our intervals already set up for us here. So this is nice and easy work. Find your ordered pairs from the table. When time is 0, the position is 0. When time is 3, the position is 46.5. I skipped over something that I should probably mention. The table below shows the position of a motorcyclist after accelerating from rest. Okay, I probably should mention that. It's a motorcyclist and they are accelerating from rest. Okay. So let's do slope, which is 46.5 minus 0 over 3 minus 0. And that is 15.5. What are the units? Feet per second. 2 more of those. Okay, I suggest you pause and try them. I'm going to pause as well. I'm going to put my answers up and then I'll come back and show you. All right, I'm back. Here are the answers to the other parts of part A. Again, it's just setting up ordered pairs and doing slope, which we have done a lot of in this class, right? Here's some more. All right, next, part B says estimate the instantaneous velocity of the motorcyclist at t equals 3. All right, so let's talk about this. We're asked to find an instantaneous velocity at one particular point. We're focusing on t equals 3, and so typically that's when we would be doing a derivative. And I can remember like way back at the end of Unit 2, I had students saying to me, why are we using approximation methods when there's an exact limit formula out there to find, an instantaneous speed or an instantaneous rate? And then it's, why are we using the limit formula when we have all these shortcuts? Okay, here's why. Sometimes we don't have a nice, beautiful equation to work with like we did in example 1 that we can take a derivative of. So what are we going to do? We're going to fall back on approximation methods or, other sorts of ways to get our answer. Now, I put a grid here for you to work with in case you would like to plot these points. This would be T and S, so that you can see a good picture of the curve that's involved in this problem. Okay, you could label your t-axis, you could scale it by ones, right? 1, 2, 3, 4, 5, 6. I don't really need to keep going, but I will. That's a 10 right there. Not that it matters. Okay, we need to go all the way from 0 to up to 180 on this axis, so maybe by 20s would work. I'm going to pause and do that. All right, I'm back. You might need to pause if you need to get caught up. So I labeled my S-axis by 20s, and then I just decided while I was paused to go ahead and plot the points from the table and draw a curve of best fit through them, and that's what I got. Okay. Now the reason that might be helpful is because we need to do an estimate for the instantaneous velocity, or we could call it the instantaneous speed here, of the motorcyclist at time t equals 3, which is the equation of the tangent line. Okay. Now, what I usually like to do with this, but it's so much easier to do in person, and I actually physically show my students how to do it, is I like to take a ruler and draw the tangent line at t equals 3. And then I also like to consider a couple of different intervals of secant lines that I could work with to see which one would be the best estimate. Okay, so here's what I mean. If I'm trying to estimate the instantaneous velocity of the motorcyclist at t equals 3, you may remember, like way back in Unit 2, we used to call that, okay, let's go in the interval from 3 to 3, which we know we can't actually do. So let's go, to a closest interval we can get to that. In this case, because we don't have an equation to work with, the closest intervals we can get to that are either 2 to 3, 3 to 4, or 2 to 4. Okay, those are our possible intervals that we could work with that would give us good estimates for the instantaneous velocity at t equals 3. Because those are the only points in time we have. We have 2, 3, 4. We don't have numbers like 3.1 time to work with. So, these are our options. And so, again, what I typically do, I don't know if you can see it on my paper here, but I like to draw the equation I like to draw the tangent line. I like to then draw the secant line from, which we would say like 2 to 3, the secant line from 3 to 4, and the secant line from 2 to 4, and see which one most matches up with the tangent line at t equals 3, or one that's parallel to, or closest to being parallel to. Okay, I'm not going to waste your time or my time on this video in trying to draw those lines. I am just going to tell you that this one ends up being a pretty good one. Meaning, if you draw the tangent line at t equals 3, and you draw a secant line from t equals 2 to t equals 4, they're pretty much parallel. Okay, so that means that if you did the slope from 2 to 4, you would have a pretty good estimate for the instantaneous velocity at t equals 3. Now, it's not always the case that you can just go on either side to get the best estimate. Getting the best estimate, could be different based on the curve, the shape of the curve. So again, that's why I like to draw those lines and see which one usually wins. Okay. So what I'm going to do here to finish part B now, after all of that explanation, how many of you just skipped like all of that explanation, is write 2 ordered pairs and do slope. Okay, I'm going to do the slope from this point to this point, and that is going to be a pretty good approximation of the instantaneous velocity at t equals 3. That's a 2 right there. And let's see, this is 58.6, and this is 2. And when we divide those, we get what, 29.3. I don't know why, you probably can't see that anyway, huh? Because my picture's there. The answer is 29.3. Okay? I trust that you can get that. I'll write it up here though. What is it again? Feet per second. There we go. Now, I'm not going to spend too much time on this part, but I just want to show you something. I'm such a nerd, a math nerd, that oh my gosh, like I actually can't believe I did this. I put this table into my calculator. Okay. I then graphed it. I did my plot and graphed. And I was like, okay, yep, that looks like what I expected. But then I went ahead and I did a quadratic regression because it looks like a parabola. It's motorcycle is accelerating, so it is a quadratic function. And that's what I got. And then I went ahead and wrote that as a function. I wrote 4.739x squared plus 1.154x minus 0.4. That's my quadratic equation that would fit that curve. And I took its derivative and I plugged in 3. I did all that work just to see that it was a really close answer to that. I got 29.6 feet per second when I did a quadratic regression, took a derivative of it, and plugged in t equals 3. Like the whole time I was doing it, I was like, I can't believe I'm doing all this, but I can't wait to see how close I am to the answer. Like there's an actual answer. All right. Yay, example 2 done. Table version done. Let's go back to an equation version here with example 3. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160t minus 16t squared after t seconds. Okay, before we look at the questions, I just want to mention that if you have the launch velocity, then you could come up with this position equation on your own using those kinematic equations, okay, but it's here given to us, okay. We're starting at like ground level, so we would call that 0. This is taking into account the launch velocity, and this minus 16t squared is actually taking into account gravity, which is 32 feet per second squared, okay. The formula uses 1/2 times that. Okay, there it is. All right, again, what we are going to do, since we're given an equation, is we're going to look at what we are asked for and look at what we are given, if we're given anything. So in A, we are not given anything other than this equation to work with and the question, how high does the rock go? How high means we are trying to find a position, right, or an S value. S gives the height, right? So we are trying to find a height here, which is an S value. Now again, we're not given anything except for the equation. So there's 2 routes you could take here. You could graph that equation if you have your graphing calculator handy and find the maximum. There are other ways to find a maximum algebraically. You could use those. Or, this is what I want to focus on. If it is reaching its highest point, okay, I want to draw a little picture. This is one of my favorite things to do in this set of notes. All right, we have the ground. Try it again. We have the ground. We have, never mind, it's just going to be sideways ground. We have the rock on the flat ground. There we go. And there's a dynamite blast. Watch this. It's my favorite part of this whole section is just doing that. It looks so bad. This is a rock, okay? It's dynamite is sending it up, up, up in the air to a highest point, and then it's going down. Okay. So what did I want to say about that? Oh, here's what I want to say. When it reaches its highest point, it changes position, right? It goes up, then it comes down. I tried to point this out a couple of times at the beginning. Here, nope, here, you have a maximum value when it changes position. Okay, so that's one thing you could think of is finding the maximum point of the graph. Or, oh, I just passed it here. At that point where it changes position, changes direction, the velocity is 0. Okay, so what am I getting at here? Let me finish my point. My point is, the way that I'm going to do this problem is I am going to take the derivative of this, which would give me my velocity. Okay, the derivative of s is 160 minus, use power rule here, 32t. Next, I'm going to set that equal to 0 because I know when it reaches its highest point, it's a velocity of 0 before it comes back down. Okay, if I solve this, solving that's pretty easy. We'll get t equals 5, right? That tells me the time that it reaches the highest point. Now, that's not my final answer because remember, we're looking for an s value. To find that s value, however, we can plug that time in. So now we are just finding s of 5, which is 160 times 5 minus 16 times 5 squared. And doing that calculation, we will get 400 feet. And that's our answer. That's how high the rock goes. It goes 400 feet. Woo! All right. That's embarrassing. This thing is embarrassing. That's like, get it off the screen, please. It's so bad. All right. I'm going to leave it on there for a minute, though, because I want to label that the highest point is 400, because then what you're being asked in Part B will make sense. Part B, what is the speed of the rock when it is 256 feet above the ground on the way up? Is it moving at the same speed when it reaches 256 feet above ground on the way down? So since we know that the highest point the rock reaches is 400 feet, we definitely know that it reaches 256 feet on the way up at some point, and it's going to pass that level again. Let's just say it's right here on the way down. So this is like our 256-foot marker, and, we're going to find the time that it hits right here and here. Okay, I'm kind of giving away too much, I think, right now. But then we'll use that to find the speed. Okay, I'll just say we're trying to find speed, right? Which is the absolute value of the derivative. So let's start with velocity, and then we'll just, take the absolute value of it. Let's try to find velocity. We have our velocity equation, but to calculate a velocity, we need time. We need a point in time to do that. So we need to find a time when it hits 256 feet going this way and this way to be able to calculate those velocities. So before we do anything with this, let's hold on to this. We need to fill 256 in, what we are given for s. That is an s value. So I look at what I'm given and I say, where can that go? It has to go in for s. I'm putting it here. When I put it there, I can solve for t, and that's good because then I can plug those times back into my velocity equation, which is what I need. All right, solving this, I'm going to add the 16 over, subtract the 160t over, keep that positive 256 there, set it equal to 0. Believe it or not, this is factorable. There is a greatest common factor of 16 that we can divide out. 16 there. And then we could keep factoring. Which just is nice and clean, and I like that. So I'm going to go that route. Instead of quadratic formula, that's another route you could go here, or graphing the parabola and finding the zeros. You don't have to factor, but I kind of like it. So when we set these factors equal to 0 and solve, we get t equals 2 and t equals 8 are the 2 times when it hits this 256 feet mark. So that makes sense, right? We hit it going on the way up after 2 seconds, and then after 8 seconds on the way down, and 5 seconds, remember, was up here at the top. It's all coming together and making sense, I hope. maybe not, because it's a lot. It is a lot. So here's what we now need to do. We're going to take these times and we're going to sub them in for our velocity one at a time. So let's find v of 2. And we get there 96 feet per second. And let's find v of 8. And we get negative 96 feet per second, which means the speed is 96 feet per second. And that is in both directions. Can you read that? You read this as speed. Okay, absolute value of velocity, you can call that speed. That's typically how we denote speed, and it is 96 feet per second in both directions. Yay! Example 3, done. 2 more. Let's take a look at example 4. For these last couple of examples, we need to be able to answer questions or problem solve when given a graph. And so that's what I want to focus on here. What we are looking at in example 4 is the position of a particle moving along the horizontal coordinate axis. Okay, so keep in mind that you are given a position versus time graph, which is what we've been dealing with throughout. However, that's important because in the last example, we'll be looking at a velocity versus time graph. All right, so let me tell you a little story about this particle. I can tell you all about it. It starts at a position of -4 on the axis, and it moves to the right to -2. Then what happens is it stays for a while at that position. It's happy there. It likes -2. Do you see how the position is not changing over the time interval from 1 to 3? It's just sticking here, staying here at a position of -2 inches. Then it starts to move again. It moves right again to a position of +2. It kind of likes +2. It stays there for a second. But then it decides, you know what, I'm going to move back. I'm going to move left, back to -2. That's its story. Isn't that cute? And I can tell you that story because what I'm doing here is I'm reading the y coordinates to, tell me the position of the particle at each moment in time. That's how you can read a position versus time graph. Now that I've told you that story, maybe you want to pause and try to answer these questions for yourself. Okay, I'm going to answer them with you though right now. First question, when is the particle moving to the left? Okay, it's moving to the left when the slope is negative, you could say, or, when it's going down. It's going from a position of 2 to a position of -2 here. That's moving to the left. And so we're going to give that as the interval from 5 to 7. Okay, we're going to say from time 5 to time 7. Now I'm going to use interval notation, and typically what we do is if it's an interior point, we use a parenthesis to not include it because it's a changing point. But if it's an end point, we use a bracket to include it because it's not really a point of change. Okay. Part B, when is the particle moving to the right? It's moving to the right when the slope is positive, or there's 2 places here. Remember I said it started at -4 and it moved to the right to -2. Then it stayed there for a while, and then it moved to the right again at time t equals 3 to t equals 4. So we have 2 intervals here. 0 is an end point, so I'm going to put a bracket around it. And I'm going to go to time 1, put a parenthesis, because 1 is a point of change. Okay, I'm going to union that with, the next time it starts moving is time 3, and it's moving to the right again until time 4. Finally, when is the particle standing still? It was standing still here for 2 seconds, right? It liked a position of -2. When it does not change position, it is standing still. It was also standing still here at time 4 to 5. And so let's do 2 intervals of time here. They're all interior points, so we will just use parentheses. We'll say from 1 to 3 and 4 to 5. So keep in mind that my little story focused mostly on the position, okay? However, it's asked, or what we're asked here is when, which is the times of those, particular movements. Okay, finally, how you read a velocity versus time graph will be different, okay? This is something that sometimes is very tricky for students to do, to be able to switch their brain from a position versus time graph type thinking to a velocity versus time graph type thinking. But I'm going to show you how to do it pretty easily. Okay, let me tell you the story of this particle. It's moving along a horizontal coordinate axis again, but this time I don't know where it starts because I'm not looking at a position versus time graph, I'm looking at velocity. But I can tell you from wherever its starting point is, it is moving to the right until this time. And then it changes position and it's moving to the left from t equals 1 all the way to this time. Why? Positive velocity means moving in one direction. Negative velocity means moving in the other direction. So when your velocity is positive, which is here and here, it's moving to the right. When your velocity is negative, which is all in here, it's moving to the left. Okay, keep in mind, you're not looking at a position versus time graph anymore. You're looking at a velocity versus time graph, and that's how you read direction from the sign, from the signs of the velocities. Positive velocities mean moving in one direction. Negative means moving in the opposite. All right, so now we can easily answer A. When is the particle moving to the left? All in this interval from 1 to whatever this time is. I just called it 4.25. It's a little bit past 4, and put parentheses. That is an interval from 1 to 4. All of this is the interval I'm looking at. That's an interval from time 1 to time 4.25. When is the particle moving to the right? It's moving to the right from time 0 to 1. And from time 4.25 all the way to 6. But wait a minute. Is this moving? I thought horizontal meant standing still. Horizontal means standing still when you're looking at a position versus time graph. However, horizontal on a velocity versus time graph just means constant velocity. It's still moving right there. Okay. For it to be standing still, it has to be a velocity of 0. So yes, all the way from this point to this point, it is moving, and we would say to the right because the velocities are positive. So now part C, when is the particle standing still? The only places where we have a velocity of 0 is instances of time t equals 1 and t equals 4.25. All other times it's moving, so we can't give an interval here. And really what's going on is that it's reversing direction. It's changing direction there. Okay, finally, when is the particle speeding up? When is the particle slowing down? When is it moving at a constant speed? Okay, I'm going to tell you, there's so many different ways you could look at this to answer the question, and I'm running out of time here, so I'm going to tell you what I think about it, but you have a lot of different options. Okay, first of all, you could go back to this cool thing that I said may be helpful, and this information tells you about speeding up and slowing down. You have to be really good at reading the graphs, though, to be able to use that. Another thing you could do, which I'm not going to take time to do right now, though, is you could draw the speed versus time graph, and it is the absolute value of this, which would take those negatives and flip them across the t-axis so that they would all be positives. Okay, and then when it goes up, speed goes up. When it goes down, speed goes down. The other thing you could do, though, is you could say the particle is speeding up when it is moving away from a velocity of 0 And it is slowing down when it is moving toward a velocity of 0. That's what I like to do. So let me show you what I mean. From time 0 to 1, it is slowing down because the velocities are going toward a velocity of 0. So 0 to 1 will go down here. From 1 all the way to right here, 3 is speeding up. And the reason I know that is because my velocities are moving away from a velocity of 0. So from 1 to 3, I'm speeding up. My particle is speeding up. From 3 to 4.25, it's going toward a velocity of 0. So it is slowing down. And finally, from 4.25 to 5, it is speeding up because it is moving away from a velocity of 0. Finally, from 5 to 6, remember we talked about that's not standing still, it's moving, but that's our answer for F. When is it moving? At a constant speed, 5 to 6. Whew, okay. If that is tricky, I promise you that if you're one of my students, we will be doing a lot more practice in class together on being able to read these types of graphs, okay? As usual, I hope this video was helpful, and good luck in your studies. Bye.